The next topic is unit vectors. Any vector of unit magnitude is called a unit vector. That's just the definition. It can have any direction, but the magnitude should be 1, the real number 1 of course. And if you have any non-zero vector v, then the following vector is a unit vector, which is obtained from v by dividing by its magnitude, dividing v by its magnitude. And not just that, it is a unit vector having the same direction as the original vector v. Let's see how. So this is the reason. First of all, since the given vector is non-zero, so its magnitude is a positive real number. In particular, the magnitude is non-zero. That means its reciprocal exists, which is also a positive real number, and that's how you can multiply the given vector by that reciprocal. This v divided by its magnitude actually has this meaning, that we are multiplying this vector by this real number. And this product of course is our usual scalar multiplication. Alright, so that is why this makes sense. Also, and now next we come to the magnitude of this vector. Now if you go back to the definition of scalar multiplication, there itself the magnitude of a scalar multiple like this, where you have a vector multiplied by a real number, is this. That is the absolute value of the real number, that is the scalar, which in our case is 1 divided by the magnitude of v, times the magnitude of the vector, which is just v. Alright, so just now we noted that this is a positive real number, so its reciprocal is also a positive real number, and that is why by the definition of absolute value of a real number, this absolute value is the real number itself, and along with that we have this as well. So after cancelling these two things you get 1. So yes, this is really a vector of magnitude 1. But what about the this remark also, that the direction of this is the same as that of v? That comes again from the definition of scalar multiplication. When you multiply a vector by a positive real number, then the direction of the scalar multiple is by definition the same as the direction of the original vector. From there this one comes. Next we have basis sets. Suppose a and b are two non-zero vectors with the direction of b neither the same nor opposite to that of a. Let OA and OB be representations of these vectors a and b respectively. Geometric representations of course you already know. And let P be the plane containing the triangle OAB. Okay, so let's now see what all these things are. So A and B are two non-zero abstract vectors having some geometric representations OA and OB, which you can see in this diagram. Okay, because they are both non-zero, so the line segments OA and OB have some length. They are not points of zero length. Moreover, the direction of B is neither the same nor opposite to that of A. That condition also you can see is being satisfied in this diagram. The direction of OB, that is this direction, is neither this direction nor that direction. Okay, so they are something like this. OB may be like this also, depends on the actual abstract vector B. Alright, and the author has also named this plane P. There is actually no need to use the word triangle here because we anyway don't have anything to do with triangles. It's just a way of expressing this situation. You can also say like this: let P be the plane containing the 3 points O, A and B. Now besides the vectors A and B, you also see another abstract vector V, okay, which is some vector whose geometric representation is OV. I mean, if you start it from O, then it is OV. What is this? Now next we are coming to that. And that thing is this. Now any vector V, any abstract vector V whose representation OV lies in the plane P can be written in the following form: V equals lambda times A plus mu times B, where you of course understand that this lambda and mu are scalars, they are real numbers and which we are calling coefficients, and where these coefficients lambda and mu are unique. How exactly do we know this? Let's try to see that in this diagram. You look at this diagram, which is just this one but with some extra things. So we still have OA and we still have OB, we haven't just written A and B. Now what we next, and we of course also have V. Now what we next do, we extend OA like this and we also extend OB. And then also we draw lines parallel to the given vectors OA and OB, both of which pass through the terminal point of the vector V. That means this line is parallel to OB and it is passing through this terminal point, that is capital V, and this line is parallel to the vector OA and passes through again V. Okay, so that we have this parallelogram. Alright. Now the original vector was OA, but this slightly larger vector OD, how will it be related to OA? It has the same direction as OA, but the magnitude is not the same. However, you can clearly see that the magnitude is some scalar, some positive real number times A. In this case positive, in some other case it may be negative. Okay. We will go to that afterwards. Let us first see this case. In this case the vector V is like this, so we needed to extend OA in this direction. Okay. So now the vector OD has the same direction as A, but it has a different magnitude than A. However, obviously because this length is something and this length is slightly smaller, so some multiple of this smaller length will be equal to this length OD. So let that be lambda. So the vector OD is lambda times A. Similarly, we also had to extend the vector OB like this, and here you have got this point of intersection E of this line and the extended line OB. Now the vector OE similarly has the same direction as B. B is this, but a different magnitude. So that is mu times B. And now you apply your definition of vector addition. Because you can translate a vector parallel to itself keeping the direction intact to have another representation of the same vector. So the vector OE and this vector, both of which are pointing in the same direction, are the same. They represent the same abstract vector which is mu B. Okay, so this is lambda A and this is mu B. So by the definition of vector addition, lambda A plus mu B is your V. So that's how you have V equal to lambda A plus mu B. And from the given situation, you will be easily able to understand why lambda and mu will be unique. Why there cannot be another set of lambda, say lambda prime and mu prime, for which also this equation would be true. No, there will be only one lambda and only one mu. Once you are given A and B and once you have chosen this vector V. Now let me also tell you a little about what I said just now, that in this case you had to consider OD, but will you ever encounter a case where say you will have to consider say a negative lambda? Here we said positive lambda, right? What about the case where your vector V starts at O but it goes in this direction? In that case you would need not just to multiply by a negative lambda, but it need not be minus 1, okay. It is some negative lambda. You will need a vector in that direction and along with this one that will give you a new V, again as a linear combination like this. We call an expression like this a linear combination of A and B, where A and B are present but not as they are, but their scalar multiples are added. Okay, so that is the linear combination of A and B. Depending on what vector V you are choosing, you may have to also consider negative coefficients. So you try to think of it yourself that if in place of this V, you have a V which emanates from O and goes in this direction, in that case you are forced to consider a negative lambda. That is because in that case, in order to have a sum like this which would give you that V, your lambda A should point in that direction. You try to think of that, why we need that direction. But this is the fact that no matter what V you are choosing, if its representation OV, representation OV means we are assuming that the starting point of the representation is O. If the representation OV lies in the plane P, what does that mean? It just means that O is of course O, it's already in the plane P, but V is lying here, V is not here or on that side of the board. Okay, that is the meaning. So if that is the situation, no matter what V is, no matter in which direction it is pointing or what magnitude it has, there will be unique lambda and mu for that given V and for this chosen system of vectors A and B, such that V equals lambda A plus mu B. And you see that it's a little, I don't want to say striking, but it's a very nice thing that just given two vectors A and B which satisfy the condition that they are not parallel, that they are somewhat like this, any vector in that same plane can be represented as a linear combination of A and B with also with coefficients which are unique for that chosen vector V. Now next we have the notion of coplanar vectors. Vectors that have their directions parallel to the same plane are called coplanar. It sounds like a simple statement, but let's try to figure it out. You have some abstract vectors in space in whatever way they can be. Now you think of their geometric representations as directed line segments, alright. So the directed line segments are in space according to what vectors they are representing. They have some directions. Now if all these directed line segments can be translated parallel to themselves, translating a vector parallel to itself does not change it. The representation changes, but the abstract vector which lies behind these representations, that does not change. Okay, so you have abstract vectors, you then consider their geometric representations which are directed line segments in space. Now if they can be translated parallel to themselves and brought down on a single plane, brought down means brought together, okay, and those translated representations lie on a single plane, then the original abstract vectors are called coplanar. With this new term, we can express whatever we found here somewhat more compactly like this. So any vector coplanar with those two vectors A and B has a unique representation of this form. Okay, so that's what we have found here in this discussion. We also have this observation about what we saw just now. Also, it's clear that the number 2 corresponding to those two vectors A and B can't be brought down to 1. In what sense? In this sense. That say whatever we found about the ability to express all vectors V in that plane as linear combinations of A and B, you will no longer have that ability if you say remove one of the vectors, say B, and consider only the vector A, which is non-zero. Okay, so say its representation is this in this plane. There are other representations also, but say we are choosing this. Now is it still the case that if you consider some abstract vector V, any vector whose representation OV lies in this plane, that is also expressible like this. Now there is no B, so what about having V as lambda times A? Is that possible? No, that is no longer possible. Why? That is because this scalar multiple can only give you vectors which either point in the same direction as A or which point in the opposite direction as A with different magnitudes, but it will never give you this. So we see that we need another vector besides A, and that too not just any vector, it should be a vector which itself is not pointing either this way or that way. You remember that condition, that the direction of B is neither the same as A nor opposite to that of A. So the number 2 seems to be somewhat special, that we need two vectors to have this ability to express every vector in the plane as a linear combination of them. The number 2 in that sense is sufficient for producing all vectors in the plane using only two vectors, but it's also necessary. If you drop one vector, then you no longer have this property. For these reasons, we call this set consisting of those two vectors A and B which are non-zero and with the property that they are like this, they are not parallel to each other, a basis set for vectors lying in the plane P. And the author also makes this part more clear. We cannot really say that an abstract vector lies in a plane. Vectors lying in P has that meaning, that if you think of geometric representations of those vectors about which we are talking here, then those geometric representations can be translated parallel to themselves so that the new translated versions lie on this single plane in that sense. Do you notice one thing? That we seem to have something special about this number 2, and we also very casually often call surfaces like this two-dimensional surfaces. A similar thing happens with three vectors. Let's see what this part says first. Let A, B and C be three non-coplanar vectors this time. Then for any vector V without any restriction, in the previous case we had the restriction of V lying in the plane P, in this case just about any vector in three-dimensional space. For any such vector, there exist unique scalars, unique real numbers, lambda, mu and nu, such that V equals lambda A plus mu B plus nu C. In order to see why this is true, you can go through a similar process that we went through in the case of two vectors, but now considering the entire thing in three-dimensional space. Actually, you already know this from your some course that you went through on vector algebra. In this case, this set consisting of the three vectors A, B and C is a basis for all three-dimensional vectors because they alone can generate all vectors like this as linear combinations. And the reason that we need three vectors to generate all possible vectors that we can think of in our discussion is the reason that we call this space three-dimensional space. If you drop any one vector from here, then you are back with that case where you can only generate vectors in plane, two-dimensional plane. And if you just simply have one vector, then the only vectors that you can generate as linear combinations of that one vector means just scalar multiples will be a one-dimensional space, because if you multiply say A by lambda, if lambda is positive and A originally points in this direction towards me, then lambda A will also point in this direction. Now by changing the value of lambda you can get vectors of all possible magnitude, but if you choose negative lambda then you will get those vectors. However, you are only able to generate a one-dimensional line. With two vectors you can generate a two-dimensional plane. With 3 vectors you can generate 3-dimensional space. In what sense? In this sense. And we can then also choose such bases with more convenience. Usually it is convenient to consider a basis set consisting of vectors that are unit vectors and which are also mutually perpendicular to one another. That means in a general basis the vectors need not all have length 1, but say we choose such a basis where all the vectors are having, I should not perhaps say length 1, magnitude 1. Say all of them have magnitude 1, that means they are all unit vectors and also they are perpendicular to one another. That means if one of them is like this, then or I can show it like this. Okay, one of them is like this, the other one is like this, and the third one is like this. If you choose any two of them, they are perpendicular to each other. This one and this one, they are perpendicular to each other. These two are also perpendicular to each other. So such bases are used extensively because they have many nice properties and they have a name also. They are called orthonormal bases. We say that some vectors are orthogonal, or say two vectors are orthogonal when they are perpendicular. Of course, you cannot think of abstract vectors becoming perpendicular to each other, but being perpendicular means that their directions are perpendicular to each other. Okay, in that sense. Or you can say that if you think of geometric representations of these vectors as directed line segments, then those line segments are perpendicular to each other. And normality has to do with them being unit vectors, that is them having unit length.